Okay, last time we discussed integral domains. Let's go over the definition and some of the theorems that we did last time before we start today's lesson. Okay, by definition, an integral domain D, usually denoted by D, is a commutative ring with unity which is different from zero. So we are disregarding the trivial ring and containing no zero divisors. So it's a commutative ring. What do we mean by a commutative ring? The multiplication is commutative because we know already that addition is commutative in any ring. And it has unity, it has one, the multiplicative identity. Not only that, contains no zero divisors. So there are no zero divisors. The ring of integers, ring of rationals, reals, they are all integral domains. Then every field is an integral domain, and we went over the proof. And then every finite integral domain is a field. This is what we proved. Next, every finite integral domain is a field. Then as a consequence, we saw that if P is a prime, then ZP is a field, right? So we have to start from here. Today, we will start by defining the characteristic of a ring. Characteristic of a ring. Okay. Let me first write down the definition. If you take R to be a ring, let R be a ring. If there exists a positive integer n such that n times a. What do we mean by that? Where a is an element in the ring, n times a, which is simply a plus, we are actually adding a n times. So this has n terms in this summation, n sums. For each a in the ring R, right? Then in R, then the least such n, the least possible n is what we call the characteristic of the ring R. Then the least such positive integer is called the characteristic of the ring R. Of the ring R. If you can't find no such positive integer, then we say that the given ring R is of characteristic 0. If no such positive integer exists, then R is said to be of characteristic 0. Okay, let's go over the definition once again. R is given to be a ring. For each element in R, if you can find a positive integer n, so that, n times a, which is given by a plus, so we have n terms in this summation, is equal to 0, I have missed that part, is equal to 0, then the least such n is what we call the characteristic of the ring R. For example, now observe that we have to, the formal definition tells you this has to be true for every element A in R. Every element A in R, right? As an example, let's take a look at this Z4, which is given by the elements 0, 1, 2, and 3. Right. Now, when it comes to 0, no matter how many times you add it to itself, you will end up getting the 0. So let's go to these non-zero elements, right? 0 over here is simply, it simply refers to the additive identity, right? Now, in this case, this is that additive identity. In the usual notation, it's denoted by 0. Right. Let's start with the element 1. We see that 1 addition modulo 4. 1 plus 1. This plus refers to the addition that's defined on the ring. For this particular ring, it's addition modulo 4. This is given by 2. Right? So this is not equal to 0. So what I'm going to do is, I will add another one to this one. So we are adding 3 of these ones. Addition modulo 4, that is. What you have is 3. Then let's do. Now you are adding 1 4 times. You get 4. Divide by 4 and take the remainder. What you have is 0, because 4 is divisible by 0. Now you see, this tells you 4 times 1 is equal to 0. So this is our n at this point. Right. Now let's go to the other element, 2. We have 2 addition modulo 4, 2. 2 plus 2 is 4, divisible by 4. Therefore, this is 0. This tells you 2 times 2, this is our n now, is equal to 0. Right? Now, observe that we are supposed to find the least integer, where n times a is equal to 0. The smallest possible n when you consider each and every element in the ring, right? Now over here, we have only considered 2 elements. For 1, the n value, or the value of n, is simply 4, not 2. 2 times 1 is simply 2. 4 times 1 is, however, 0. Right? Now, but when it comes to 2, 2 times 2 is 0, but also 4 times 2. That means you are adding 2 4 times. What you get is 0. So if n over here is replaced by 4 for the element 2, we once again get this to be 0. Now let's go to element 3. 3 addition modulo 4, 3. Is equal to 2. 3 plus 3 is 6. Divide by 4, you take the remainder, you get 3. And this is not equal to 0. So let's do 3 plus addition modulo 4. This one. What do we get? 9 divided by 4, take the remainder, you have 1. Now, the other case, when you add 3 4 times, this gives you 12 divisible by 4. Therefore, this summation ends up being 0. So this gives you 4 times 3 to be 0. Now this integer 4 works for each of these elements. 1, 2, 3, and certainly, definitely we have 4 times 0 to equal 0 as well. Right? And this is the smallest possible n. 4 is the smallest possible positive value. That gives you 4 times a to equal 0, where a is any element in Z4. Obviously, for 2, you can simply take n to be 2, but this particular value, 2, does not work for any other value, any other element in the set. 4 does for every other element, every element in the set. Therefore, the smallest positive integer n such that n times a equals 0 for a element in Z4 is 4. Therefore, the characteristic of Z4 is 4. Right? Now, obviously, if the ring is too large, if it contains an infinite number of elements, this checking for each element would be impossible. Right? But there is a way to go about it. Before we go to this one, let's take a look at another example. Let's take Z, the ring of integers. I'll take any non-zero value of Z. Let's take 2, 2 in Z. Can we find some n? Do we have a positive integer n such that n times 2, which is simply 2 plus 2 plus the usual addition, where we contain n terms over here, is equal to 0. N is positive, right? It's non-negative. It's positive, not 0 or negative, right? Can we find such n for this one particular element? No, we cannot. If we start with the smallest possible value for n would be 1, smallest possible value, because n is a positive integer. So when you put 1 over here, 1 times 2 is simply 2, not equal to 0. And the next case, next possible number would be 2. 2 times 2 would be 2 plus 2. That also equals uh, 4, not 0. And we can see that this summation will actually never go to 0. This summation will never go to 0 for any positive integer n. Therefore, you can't find for any non-zero, for any non-zero integer, you can never find such n. Right? You can never find such n. So what does it mean by definition? The characteristic of the ring of integers is simply 0. For any positive n. Therefore, the characteristic of Z is 0 by definition. It's 0 by definition. Okay. Now, like I said earlier, if the ring is large, containing a lot of elements, it's impossible for us to check for each element one by one, right? But for us to actually determine the characteristic, we only have to check when A is equal to 1. We only have to check for the element 1 if the ring contains unity 1, which is different from 0. Right? Okay. Then let me first write it. To determine the characteristic, we only need to examine A equals 1 if the ring R contains 1. 1 is unity. If the ring R has unity 1, which is different from 0. Okay. We have given this as a theorem. Let R be a ring Let R be a ring with unity. If n times 1 is not equal to 0 for all n in for all positive n's, let's put it like this, z plus, then R has characteristic 0 if n times 1 is equal to 0 for some positive n, then the smallest such n is the characteristic of R. Then the smallest such n is the characteristic of R. Then now the definition tells you for every element we have to check for this condition. When this 1 is replaced by A, any element in Z. And in that case, we pick the smallest such positive n, and that would be the characteristic of R. If this is true for every element in the ring. On the other hand, if for at least one element we don't have n times that element to equal 0, then we know the characteristic of that ring is 0 by definition. Right? How do we prove this? Now the theorem tells you don't actually have to go looking for all the elements in the ring satisfying this condition, or at least dissatisfying it, to determine what the characteristic is. You only have to look at this unity if the ring contains it. Okay. Now let's suppose if n times 1 is non-zero, right? That means there is at least one element which is simply 1, where n times 1 is not equal to 0. By definition, the characteristic has to be 0. So this first half is somewhat evident just from the definition, right? So we write if n times 1 is not equal to 0 for all the positive n values, right? Then we do not have n times a to equal 0 for all a in R, right? Uh, then we do not have n times a to equal 0 for all a in R for some positive n. Because for this particular one, n times 1 is not equal to 0 for every n, right? For some n positive value, right? Then by definition of a characteristic, R has characteristic, R has characteristic 0. Now suppose for some n, we have n times 1 to equal 0. Such that n times 1 is equal to 0. Now let's take any element A in R. To use the definition, we had to show that for any element, for an arbitrarily chosen element A in R, n times A is also 0. That's what we have to show. Let A in R be arbitrary. Then we have A times n, which is simply A plus all these summations. We have n terms in this summation. Now, what do we do? Using distributive laws in a ring, we sort of factor out A. We have A 1 plus, how many terms are there in this summation? N. So we have A n times 1. We have A times n times 1. Now we know that n times 1 is 0. So we have A times 0. We know that from a previous theorem, we have proved this. This is equal to 0. And we are done. Right? A is chosen arbitrarily. For any element that you take from the ring, that element times n is equal to 0. So by definition, therefore, by definition of a characteristic, R has characteristic the smallest such n, okay? The smallest such n. So if we take this n to be the smallest n such that n times 1 is equal to 0, that we have to state over here. And for every other element, this works, which is true. By definition, R has characteristic n. Okay. Now, if we go back and look at some other examples, let's put it over here itself. If you take Z7, this contains elements 0, 1, 2, 3, 4, 5, 6, 7. This is a ring, not just any ring, it's a field as well, right? Now, it contains unity 1, right? It's a field, so it definitely contains the unity. Now, let's see. 7 times 1 is simply sorry, not just 7 times 1. If you start with n equals 1. We have 1 which is not equal to 0. So we start and then we move to n equals 2. 2 times 1 is simply 1 plus 1, which is 2. When you add 1 3 times, you get 3. When you add 1 4 times, you get 4. And going in this direction, we see that when you add 1 7 times, which is simply 7.1, you add 7, sorry, you had 1 7 times, what you get is 0. Because 7 times 1 is 7, divisible by 7, therefore you get 0. Therefore, the characteristic of this ring is simply 7. If you go to the previous example, the characteristic of Z4 is 4. So we see that the characteristic of Zn for any positive n, is simply n, because you have all these rings contain the unity 1, and n times 1 is equal to 1 when that, sorry, m times 1 is equal to 0 when that m is simply equal to the number of elements over here, so n. Right? It's easy to see that. Okay, now with this, we are moving on to the next section. The field of quotients of an integral domain. Let me write it down. Okay, once again, what do we mean by an integral domain? It's a commutative ring containing one with no zero divisors. Okay. Now, in one theorem, we actually discussed this last time also. We prove that finite integral domains are fields. Finite integral domains are fields. But not all infinite integral domains are fields. For example, the ring of integers, right? It's not a field because it has none of the multiplicative inverses for all these non-zero elements. Therefore, it's not a field. But any finite integral domain will always be a field. Not all infinite integral domains. But any integral domain can always be contained in a field, right? And we know that Z is contained in Q, R as well as C, right? Now, Z is contained in Q, and in this instance, we call this the field of quotients of the integral domain Z, right? Why do we have this? Where does this idea stem from? It actually comes from Z and Q. So let me list down what I just told you. All finite integral domains are fields. But not all infinite integral domains are fields. Example, Z. It's a ring. It's not a field. It's an integral domain, not a field, right? Every integral domain, however, is contained in a certain field, right? For example, Z is contained in Q. It's contained in Q. And we call this field containing the integral domain a field of quotients of that particular integral domain. And how do we define this field of quotient, or how do we construct it? We construct it using this integral domain, and the construction we will do. Field of quotients of the integral domain. Now observe, to make sense of this idea of a field of quotients. You have Z to contain integers. Now what sort of elements do we have in Q? In Q we have elements of the form A over B, a quotient. Where do we get this A and B from? A and B, sorry, come from the ring of integers with this additional condition of B being non-zero. Right now you see, using elements of Z, we consider these quotients and we add this special condition where B is non-zero, otherwise this division will not be defined. And containing all these elements is the set Q, which is what we define as the field of quotients, right, of the integral domain Z. So all these elements are expressed as quotients of integers. Expressed as quotients of integers. Okay. Now, how to do the construction, we consider an arbitrary integral domain D. And for this particular D, we will find, or we will construct a field of quotients F containing in it, containing D. Let D be an integral domain which will extend to a field of quotients F. So you have an integral domain D over here. Containing this, we have the corresponding field of quotients F. I know this F is what we are trying to build using D. First, what we do is we form the Cartesian product, right? And we will, while we are doing this construction, we will see the correspondence this has to Z and Q. That way it would be easy for us to understand it. Right. Form the Cartesian product. Which contains pairs of elements of D, A and B, where A, B are elements in D. You can compare this with this one. This quotient is defined using two elements in Z. Over here also, for this pair, you take two elements from D. Now, we think of this pair as representing a formal quotient A over B, right? So if you compare this to this one, this A over B is represented by this element. So we think of it as representing a formal quotient A over B. Now, this is the same as A over B that you see in Q, right? Now, what does it mean, first of all? As an example, if you take D to be Z, then -2, 7, this element that you take from this Cartesian product will represent the quotient -2 over 7, right? -2 over 7. Now observe, just because we have this Cartesian product, just because we form this Cartesian product, does not mean all these elements that you have over here would make sense if you're thinking of it solely as representing a formal quotient. For example, if we take A to be, now for this particular example, when D is the integral domain Z, if you take the pair of integers 1 and 0, 1 and 0 should represent a formal quotient that should be given by 1 over 0, but that is not defined. It does not make sense, right? So not all elements over here would really help in constructing this field. So we have to impose some sort of restriction, right? So what we do is, before we actually get to the part, observe that 1, 0 would not represent any element. It does not represent any element. So what we are going to do is we are going to impose a condition and say you can take all pairs of elements except for the second coordinate, except for the elements where the second coordinate is 0, right? So we are going to, from this set, from this, after you form the Cartesian product, from this set, we are going to pick a subset as let S be the subset of D cross D such that S contains all elements where A, B come from D and B is not equal to the additive identity, which is denoted by 0, right? Which is denoted by 0. Now, if you compare this to this one, right? They are almost the same. You have this first element, which is expressed as a quotient, and this pair, you think of it as a quotient of A over B. The conditions are the same. You're taking the two elements from the integral domain. This element B is non-zero in both cases, right? Now we are not really done with the construction, but mostly yes. Now, observe that when you take different pairs of elements, they could represent the same. They could represent the same, right? For example, if you take when D is the set of integers, right? When you take the pair of elements with respect to this particular D, you take the pair 1, 2, and 2, 4. They represent the same element. So what we are going to do is we are going to define a relationship between, or we are trying to find when two elements would be the same in S, right? So let me write it down. Observe that uh, different pairs of elements can represent the same element. If you compare with this example, if you try to say this when the integral domain is Z, you take two elements, 1, 2, and 2, 4 in S, right? S, which we defined earlier. We know that 1 over 2 is the same as 2 over 4, right? So we could, the same, even though these two pairs are distinct, they are different, they're actually representing the same element, right? So now we are going to define a relationship or see when two elements are the same, right? We now define when two elements of S will represent the same element. Now remember, we are trying to find F, which is the field of quotients containing D, right? And we are trying to understand what type of elements this F contains. Right. We've got a definition. AB and CD in S are equivalent and we denote this equivalence by denoted by AB tilde CD. So AB is equivalent to CD if and only if and only if AD is equal to BC. right? AD is equal to BC. If I write it separately, AB is equivalent to CD if and only if AD is equal to BC. You take AD and BC. If this product is the same as the other product, BC, then we say that these two elements are equivalent, sort of represent, those are the same element. They represent the same element in F. Right? For example, now, if we try to compare this definition with Z, right? If you go back to our usual example, when you take D to be Z, uh, the usual definition of equality of two quotients, let's say, we have from the usual definition of equality for the pairs AB and CD that come from S, which simply resembles the quotients AB and C over D. B and D are, by definition of S now, non-zero, comes from Q. We have A over B to equal C over D. What does this condition give you? This gives you, when you cross multiply, AD equals BC, the same thing that you see over here. So, two quotients are equal, that is A over B is equal to C over D, if and only if AD is equal to BC, the same thing that you see over here. From this, this tells you this A over B, this pair is representing A over B in Q. This pair is representing C over D in Q. So it's basically the same thing. Right? Now, if you give a specific example, in this case, you have 1 over 2, 2 over 4. How do we know that these two pairs are the same? 1 over 2 is equivalent to 2 over 4 for this particular example. If and only if 1 times 4 is equal to 2 times 2, which is true. In other words, 1 over 2 simply equals 2 over 4. You get the same thing. Okay. With this, we get to our first lemma under this section. This given relation, which is denoted by tilde, is an equivalence relation. Defined above is an equivalence relation. What does it mean? This relation is reflective, symmetric, and transitive. So you have to prove those three. So you have an equivalence relation. Once you understand that this is an equivalence relation, we can find corresponding equivalence classes. Now these equivalence classes are going to be our elements in F, right? Before we get to that part, let's prove that this is indeed an equivalence relation. First is tilde is reflexive. What do we mean by reflexive? In order to prove this, we had to show that, A comma B is equivalent to itself. A comma B. So this element is equivalent to itself. Right. Now this is true. Why do we have this? If this is equivalent, these two elements, then we must have, by this definition, AD, in this case AB, A times B to equal B times A, right? A times B to equal B times A. Now observe that A times B is equal to B times A. For any element, for elements A and B that we take from D. Why is that? D is an integral domain. That means, sorry, it's a commutative ring first of all, right? So this commutativity of the multiplication allows us to write AB to be the same as BA, right? Observe that AB is equal to BA for AB in D, since D is a commutative ring. Since D is a commutative ring. It's an integral domain. Integral domains are commutative rings. Right? Now, AB is equal to BA. If we go back to this relationship, this is an if and only if, this is the definition. So it's an if and only if statement. Because we have AB to equal BA, that means AB is equivalent to AB, right? So I will take this, no, by definition of tilde. By definition of tilde, we have AB to equal BA. Therefore, tilde is reflexive. Tilde is reflexive. Now the other part, tilde is symmetric. Tilde is symmetric. What does it mean? What do we have to show in that case? This means if AB is equivalent to CD, then we must have, if this is true, then we must have CD to be equivalent to AB. This is what we have to show, right? If AB is equivalent to CD, right? Then we have, by definition of this equivalence relation, AD to equal BC. AD to equal BC. Now, with this information, we want to show that CD is equivalent to AB. So the definition of tilde, definition of this equivalence relation tells you, if this is equivalent to AB, that means we must have CB. Let's put it in red here. CB to equal DA. CB to equal DA. Now we have AD equals BC. I will simply write BC equals AD. We know that D is an integral domain. So it's a commutative ring. So we commute each of these elements on both sides, right? Since D is commutative, we have commutating these two. CB to equal commutating these two once again, DA. So that by definition of tilde, we have CB to be equivalent to, no, CB is equal to DA. So we have CB over here, DA, exactly what we wanted to show. So we know that tilde is symmetric. Now, to prove that last one, that it's transitive. Tilde is transitive. What does it mean? That means if we have AB to be equivalent to CD and CD to be equivalent to RS, then we must have AB to be equivalent to RS. If this is true, we say that tilde is a transitive relation. Okay. Now, let's take AB to be equivalent to CD and CD to be equivalent to RS. Then from definition of tilde, we have by definition of tilde, we have AD to equal BC and CS to equal DR, right? Now at the end, we have to show that AB is equivalent to RS. So what exactly are we showing? If AB is equal to RS, all we have to show is A times S is equal to B times R. This is exactly what we are going to show, right? Now, observe then that in each of these, in each element, A, B, C, D, in each of these pairs, RS, B, D, S, they are all non-zero. That's how these elements in S are defined. For this second element to be non-zero. If we take the pair AB, B must be non-zero if this element is coming from S. Right? Now, multiplication of D is commutative, right? Note that D is commutative, right? Therefore, we first consider the product. We want to show that AS is equal to BR, right? ASD, right? This is equal to, if you go to this, S and D, we will commute because D is commutative. So I can write A, D, or at least A and S we will commute. So we write SAD, right? SAD. Now AD, somehow we want to show that at the end ASD is equal to BRD, right? So S times AD is equal to BC. We have S times BC. Now what we do is, for BC elements in D, the product BC is also an element in D. So we consider this to be one term. We commute S with BC. We get BC times S. BC times S. Now we commute C and S. We have B, no, we don't have to commute this. Now, BCS, CS is equal to DR. So I'm going to replace this CS by DR because we want to get BR. Now we commute D and R, the two elements. We have BR times D, right? Now observe, this gives you AS times D, BR times D. D is not equal to 0. D is not equal to 0. And capital D is an integral domain, then we can use the cancellation, multiplicative cancellation laws and cancel D from both sides. D is an integral domain, so D inverse exists. D is non-zero. For all non-zero elements, the inverse exists. So we use those cancellation laws and cancel out D. What do we get at the end? AS to equal BR. Since capital D is an integral domain, and D is non-zero, we can apply multiplicative cancellation laws to cancel out D so that we get AS is equal to BR. And so, by definition of tilde, we have AR is oh sorry, BNS. Yeah, A, B, and SR. Okay, this is B over here. Right, so this proves that tilde is transitive. So tilde is reflexive, symmetric, and transitive. Therefore, by definition, it's an equivalence relation. Therefore, tilde is an equivalence relation. Now we are going to define elements in F. Because it's an equivalence relation, we can talk about equivalence classes, right? So all these equivalent elements fall under in one class. So this class, one equivalence class would be an element in F. So F contains the set of all equivalence classes that are being formed by this relation, right? So let me define F, the field of quotients containing the integral domain D, contains or is, let's put is, the set of all equivalence classes which will be denoted by, for element AB, this will be the corresponding equivalence class. The equivalence class will be denoted by this. We will simply disregard putting a bar for the element, this pair in S. Right. Now we want to show that, now we want F to be a field. It's the field of quotients containing D. First of all, we have to show that this is indeed a field. Not only that, it's containing D. Right, it's containing D. So the first lemma, in the first lemma, we are going to define the two binary operations, because if it's a field, it has to have the two binary operations must be defined on it, addition and multiplication. So what is going to be addition and multiplication defined on F? Lemma. Let's take two elements from F. So let's take this equivalence class of the element AB and the equivalence class of CD in F. The equations given by AD plus BC, BD. And AB times CD, which is simply given by AC, BD, give well-defined operations of addition and multiplication on F. How do we see that this is well defined? We can see this by example. Let's take D to be Z, right? Then the pair CD actually represents the quotient C over D, where D is non-zero. And this is an element in S. We have to take elements from S, therefore D is non-zero, right? Okay. Right. Let's take so this implies if you have A, B, C, D, from definition of S, in S, we know that B is non-zero, D is non-zero, and these would represent A over B and C over D. Now let's addition on Q is the usual addition we know. Let's add these two elements to see what happens, okay? We have A over B plus C over D. This is equal to AD plus BC over BD. Sorry, BD. Right? And this is represented by the pair AD plus BC, comma, BD in S, right? This addition is represented by this pair in S. Now go back to the definition. You add these two, what you get is an element in S, which is the same that you see over here, which is the same that you see over here. So these pairs, you can always visualize them as being a quotient A over B or C over D, whatever the pair that you pick, right? So when you add those two, and the addition gives you this, corresponds directly with this pair. So the addition is well defined. You can see it by this example. If you go to multiplication, you have A over B times C over D to equal. So what we are doing in this case is to see that these are well defined in F. We are taking one representative from each equivalence class and performing the usual addition and multiplication over Q, right? Over Z. This is AC, this is over Q, sorry, over Q. AC over BD, this is represented by AC, BD, once again in S. If you go to the definition, AC, BD, the same thing that you see over here. So this is the equivalence class of this element in S. Right, so this addition and multiplication will be performed on representatives of each equivalence class. Right. Now, some properties of this addition and multiplication. First one is addition in F is commutative, not only that, associative. So the proof of that one I will disregard. You can do it on your own. Addition in F is commutative and associative. Then we have the equivalence class of the element 0, 1 is the identity element for addition in F. So is the additive identity in F. To see this, let's take one element from F. Let's take this equivalence class in F. Then we have this element plus this other element 0, 1 to equal. If you go to the definition of addition, right? You have AD plus BC and the next element is simply BD. So you have A times 1 plus B times 0. A times 1 plus B times 0, which is 0, comma, B times 1. This is simply A, B. And similarly, we can see that 0, 1, to this element, if we add AB, once again you get 0 times B, which is 0, A times 1, which is A. So the first component is A, 1 times B is B. So by definition, yes, this element is the additive identity in F. 3. Now, if you compare this with Q, we know the additive identity in Q is 0, which can be given as 0/1, right? So 0 is an element in this equivalence class, right? Because you can write it as 0/1. Okay, now the next one, negative AB, this equivalence class is the inverse, the additive inverse really. Is the additive inverse for the element AB in F. Observe that this is also an element in F. We have this element which is in F, so B is non-zero. Over here also, if A is an element in D, negative A is also there because D is an integral domain. Negative A is there, B is also there, B is non-zero. So this is an element in F. Not only that, we are saying that this is the additive inverse for AB. To see this, we are going to add these two. This is equal to AB minus B times A. A times B, sorry, plus B times minus A, right? Comma B times B. B times B. This is equal to, now observe that A times B. This negative you can straight away take out. We have proved this in a previous theorem. So you have a negative over here. B times A. D is an integral domain. B, A, they are all elements in D. Therefore, we can write instead of B, A, B. Comma, B times B. This is equal to, these two cancel out. Sorry, 0, comma, B squared. Now, B is non-zero, right? B is non-zero. We have this element. We want this to be the identity, which is this, the additive identity in F. But this element is actually equal to this one. Why do we have this? Now, this is equal to 0, 1. This is the same equivalence class. That means these two representatives are equivalent. If they are equivalent, that means the element 0b squared and 0, 1, they are equivalent under the relation tilde. If they are equivalent, they belong in the same equivalence class. So that is exactly what we are going to show next. We are going to show that these two are equivalent. This is because 0, 1 is equivalent to 0b squared. Since if you go back to that if and only if statement, when do we say that two elements are equivalent? When you have 0 times b squared is equal to 1 times 0, which is actually equal to 0. This equation is satisfied. Therefore, those two are equivalent. So we know that we were looking at the same equivalence class, which is the additive identity in F. Right. Now the next property. 4. Multiplication in F is associative and commutative. This also I will leave to you. Then the second one, the other one, fifth one, the distributive laws hold in F, the usual distributive laws over a ring, right? The distributive laws hold in F. Then we have the element, the equivalence class, which is an element in F, is the multiplicative identity element in F. Multiplicative identity element in F. To see this, if you take any element AB in F, we have the equivalence class of 1, 1 times equivalence class of AB by definition of multiplication, which we defined earlier. We have this to be 1 times A, comma, 1 times B. This is simply AB. Right? And you can commute these two also and see the same. Because we have already said over here multiplication is commutative, you don't have to do that part. Now we have if this equivalence class, this element in F, is not the additive identity. That means we are excluding 0. 0 resembles the additive identity. So we are kind of taking out 0. We are saying that this is not 0 in F, right? Is not the additive identity. Then if this is not the additive identity element, then we surely know this first component A is non-zero in D. Otherwise, it will be the additive identity. As we saw earlier with this case, the first component will always be 0 if it is the additive identity, because the second component will never be 0 in S. In D, and in this case, BA, this element, the equivalence class of BA, an element in F, is the multiplicative inverse for the element, uh, the equivalence class of AB. Right. Okay. What does this tell you? This tells you every non-zero element in F has a multiplicative inverse. Right? If it is a field, all the non-zero elements must have inverses, multiplicative inverses. That is exactly what's being said over here. Right. Now, to prove this one, first observe, you take this one, this element in F, right? If you have A to be 0, then this will be the identity element. This we will first prove, right? If A is equal to 0, then we have um, AB, this element, to be equivalent to 0, 1, since A times 1 is equal to 0 when A is equal to 0. And this is equal to B times 0, which is also 0 because we are multiplying this non-zero number by 0. Right? So A times 1 is equal to B times 0. Therefore, AB is equivalent to 0, 1 by definition of tilde this is. This tells you if A is equal to 0, these two are equivalent. In other words, the equivalence class of AB is the same as the equivalence class of 0, 1. And we know that this is the additive identity in F, which we proved earlier. Right? So if you want this element to be not be the additive identity, we must have A to be non-zero. Then we have the equivalence class of AB to be the same as the equivalence class of 0, 1. Therefore, if this element is not the additive identity, so we're taking the contrapositive of this statement, right? Is not the additive identity. In F, we must have A to be non-zero. A to be non-zero. Now observe, so this tells you this element is not the additive identity. In that case, A is non-zero. When A is non-zero, the element BA exists in S because now B and A are elements in D and A is non-zero. Therefore, we have this element to exist in S. If it is an element in S, it has a corresponding, it has a corresponding equivalence class, which is an element in F. Therefore, we have the equivalence class of this element to be an element in F. Now, this is an element in F, right? So, it's an element in F. Now, we have to show that this is the multiplicative inverse of this element in F, which is the equivalence class of AB. So, now we multiply these two and these two equivalence classes to see that it gives you the multiplicative identity. This is equal to, by definition of multiplication defined over F, we have this to be AB, BA, the equivalence class of this element, right? Now, now we want to show that this is the same as the equivalence class of 1, 1, right? In D, AB is the same as BA. That is because D is an integral domain, it's commutative, right? Since D is commutative, we have AB to equal BA, right? So what we do is multiply both sides by 1 because we want to show that this is equivalent to 1. So AB times 1 is equal to BA times 1. And hence, by definition of tilde, we have this we can write as BA times 1, we can write as 1 times BA because D is an integral domain, right? And then by definition of tilde, we see that so AB, BA is equivalent to 1, 1. Okay. Therefore, if these two are equivalent, their equivalence classes are also the same. So we see that this multiplication actually is the equivalence class of 1, 1, which is the multiplicative identity in F. Therefore, this is the multiplicative inverse of AB by definition. Okay. So now we see that F is a field. It has all the conditions satisfied. We have to show that this contains D. We will now show that F contains D. Let's take a look at this lemma and let's prove it. Okay. So now what we are going to do is we are going to show that D is actually embedded in F, right? In order to do that, we define this map and we say that the map I from D to F given by I of A equals now A is an element in D corresponding to this A, we must have an element in F. What sort of elements do we have in F? Equivalence classes of pairs of elements in D, right? So this we will map to the element A1 in F, right? Is an isomorphism of D with a subring of F, sorry. So this is embedded in F. This is D is isomorphic to some subring of F. Now, if you look at this before we actually get to the proof, we have IA to equal this, right? In other words, A will be mapped to the equivalence class of the element A1. This is coming from D. This is coming from F, right? Now, F is the equivalence, this element in F is the equivalence class of A1. If you look at A1, which is an element in S, this one is non-zero as you can see. This represents, it represents the quotient A over 1, which is simply equal to A, right? So we see that this element is sort of mapped to itself, right? You take A and corresponding to this, you find an element in S, you take its equivalence class and you map this A to this particular equivalence class, right? Mm. So you sort of like have this way of going about it. So we can see that this is well defined. Right. Now we have to show that I given over here, this I is an isomorphism. So it has to be a ring this D is an integral domain, F is a field, they are both rings. Therefore, first we show that I is a ring homomorphism. We will show that I is 1-to-1 and it is onto its domain. It's onto its domain, which will be a subdomain of F. That is exactly what we want to prove, right? So D will be isomorphic to this subring of F. Okay. Right. First, we want to show that I is a ring homomorphism. First, we will show that I is a ring homomorphism. So the first condition is we had to show that in order to show that it's a ring homomorphism, we had to show that A plus B is equal to IA plus I of B and I of AB. We have to show that this is equal to I of A times I of B for all AB in D, right? Now to prove the first condition, let's take A, B to be elements in D. We take A and B to be elements in D. Let's calculate I of A plus I of B. I of A, by definition of this map, is given by this equivalence class of the element A1 plus B1, this element, equivalence class of B1. Now, we know addition that is defined on F. How do we add these two classes together? We get A times 1 plus 1 times B, comma, the second component will be 1 times 1. So we have A times 1 plus 1 times B, comma, 1 times 1, which is 1. This is equal to A plus B, comma, 1. And if you go back to this definition once again, you have this equivalence class of A1, and that is equal to I of A. So by definition of I, this is equal to I of A plus B, exactly what we wanted to show in the first case. Now let's go to the other one. That is I of A times I of B. This is equal to the equivalence class A1 times I of B is simply equal to this. And we know multiplication defined on F. Using that definition, we see that this is equal to A times B. 1 times 1 is 1. Once again, the definition of I allows us to write this as I of AB, exactly what we wanted to show in the second case. Therefore, I is a ring homomorphism. I is a ring homomorphism. Now, in order to show that this is an isomorphism, this is an isomorphism, we have to show that this homomorphism is bijective, right? We have to show that it's 1 to 1, but remember this D is isomorphic to some subring of F. So what we are going to do is, this map is definitely onto its range. We will simply show that I is 1 to 1. To show that I is 1 to 1, suppose we have I of, for AB in D, I of A to equal I of B. We have to show that A is equal to B. Then by definition of I, we have the equivalence class A1 to equal this, B1. If these two are equal, if the two equivalence classes are equal, that means if this is the same equivalence class, that means the two representatives must be equivalent, right? If the equivalence class over here is the same as this one, the two representatives must be equivalent. So we use that. Then we must have A1 to be equivalent to B1, so that by definition, if this is equivalent, by definition of this tilde, we must have A times 1 to equal 1 times B. That means A equals B. Exactly what we wanted to show. Therefore, I is 1 to 1. Therefore, I is 1 to 1. Now, I is an isomorphism. Now, if we consider the range, right, this is 1 to 1, then I of D will be isomorphic with I of D because the D is onto its range, right? So we can conclude the proof by saying, therefore, I is an isomorphism of D with I of D. I of D, where I of D we are done with the proof. Right, and we are done with the proof. Now, okay. Now observe this. For this particular mapping I which is from D to F, defined by I of A equal to the corresponding equivalence class, right? For A in D, right? Now, if you take that A, B, be elements in D. Now, if we go back to our very first example where D is Z, Q is the ring of resonance, the field of resonance. If you take any two integers A and B, in Q, we have this quotient A over B when B is non-zero, right? So we want to see something similar in F because F is what we defined as the field of quotients containing D and it's constructed by D using D, right? So for any given two elements in D, we want to sort of see that quotient in F, which we can do because F is a field. So we can write um, it contains elements of the form I of A over I of B. When you say over I of B, just to show it using a quotient, as a quotient, this is simply I of A times I of B, the inverse of I of B, right? And we know by definition of this I, this is the equivalence class A1. And I of B is simply the equivalence class of the element B1 and its inverse is given by 1B. If you go back to that previous property we did, uh, if A, B in F is not the additive identity, we simply switch these and take the equivalence class of BA to be the multiplicative inverse, right? Now go back to this one. B1 is not the additive identity. In that case, we say that its inverse exists. Now for non-zero elements, sorry, shouldn't say non-zero. For elements that are not the additive identity, the inverse exists. So you can take the inverse like this, right? And inverse is given by this if you refer to the previous property. And this is equal to by multiplication that's defined over F. We know that this is equal to A times 1 times B, which is B. So now you see, this is an element in F. An element in F can be represented, can be seen as this quotient I of A over I of B. So all elements in F are represented as these quotients. They are actually quotients of elements of the form I of A over I of B. So this property sort of holds in F. This is any element in F. And B has to be non-zero in this case anyway. B is non-zero. Let me specify it over here. B is non-zero, otherwise we will not be able to define the inverse. Right? So we can represent elements in F as quotients. Okay. Now, by this theorem, we conclude saying that F is the field of quotients of D. Any integral domain D can be enlarged or embedded in or extended to. A field F such that every element of F can be expressed as a quotient of two elements of D. It can be expressed as a quotient of two elements of D. Now, this I of A and I of B, remember from this theorem, we proved that this D is actually embedded in F. Okay. Okay. And we say that F is the field of quotients of D. Field of quotients of D. Okay, now I will state the next theorem. Let F be a field of quotients of D. So now we have F to be containing the integral domain D, right? Let F be a field of quotients of D and let L be any field containing D. So L is another field containing D. Then there exists a map phi from F to L that gives an isomorphism of F with a subfield of L such that phi of A is equal to A for A in D. So we start with the field of quotients F of D. Then we take another field containing D. Then we say that there is a map between these two fields that gives an isomorphism of F with a subfield of L so that phi of A is equal to A for all A in D. So phi is the identity map over D, right? Okay. So what does it mean? This means that any field containing D contains a subfield which is a field of quotients of D. So this field F is like the smallest field containing D. That is what it says. The field of quotients of D will be the smallest field containing D. Any other field containing D will contain a subfield which is simply F. So F is contained in any other field L which is containing D. We will stop from here and I will do the proof of this theorem in the next lesson.